these enzymes called CYP74 enzymes. Okay. First of all, I will tell you where I do actually come from, for those of you who aren't too familiar. So, there's the United Kingdom, there's Norwich, in the southeast of the country, in a region called East Anglia. And in Norwich, there's this collection of research institutes on what we call the Norwich Research Park. So we have the John Innes Centre here, and then we have another institute called the Sainsbury Laboratory, which is actually attached right immediately adjacent to John Innes, but it's actually funded independently by the Gastric Foundation, and we do a lot of work with them. There's another institute called the Institute of Food Research, just across the road. Then we have the University of East Anglia here, which is a very big campus, we do work with them. And then some people also work with the new hospital, the new university hospital which is built. So the whole group of research institutes all working together. And it's quite a nice environment to work in. So this is the view across one of the Broads near the university. This is the John Innes Centre. So John Innes, this is a multidisciplinary research institute. I actually work in that building there, on that floor. So there's about 900, almost 1,000 scientists and support scientists who actually work on the institute. And we are John Innes has been around for 100 years now. We celebrated our 100th anniversary last year. And it was, of course, based on plant genetics. That's what John Innes is famous for. But we do a whole range of other things, and we can translate our research from the DNA right through to the RNA, all the way through to the protein, through to products. And we have another company on site in this little house here called Hill House, which is an IP company called Plant Bioscience Limited. And then any ideas that we come up with, they can often take them forward and try to get them, into producing useful things for the public. Anyway, let's get on with the talk. So, I just thought I'd say about John Innes. So, a bit of showing off here, but John Innes the Times Higher Education Supplement did a survey for looking at publications between 1999 and 2009, and John Innes Centre came out top in terms of the number of citations per paper, which we're very pleased about, and also the scientist on 2010 rated the John Innes as the fourth best place to work in academia, which was quite nice. Anyway, so CYP74 enzymes, what are they? They're a specialised class of cytochrome P450 enzymes, and they were originally thought to be found only in plants. So how am I going to give my talk? I'm going to tell you first of all what are P450 enzymes. I'm going to talk about the functional similarities between animal and plant P450 enzymes. Then I'm going to discuss in detail a typical CYP74 enzyme, which is the one that I've been working on for some years, called microperoxide lyase. I'm then going to talk about the biology, the plant biology of the CYP74 enzyme, and about these green leaf volatiles that the enzyme is involved in making. Then I'm going to talk about how HPL is currently used in industry, and why it's a value to industry. I'll talk about the problems that have been, the problems that there are, about the new technology that we've developed and the new ideas that we can do to take this product forward. And then I'm going to talk about areas of opportunity that maybe new partners might be interested in to help develop this technology. Okay, so what are P450 enzymes? So these are a superfamily of heme-containing enzymes, or monooxygenases, that are involved in oxidative metabolism. And the reason why they're called P450 is because if you incubate them with carbon monoxide, the carbon monoxide binds to the protein, and you get a shift in the UV visible spectrum of the protein to 450 nanometers. You get a typical peak here. So this is the actual spectrum of the HPL that I work on. P450 enzymes are found everywhere, so they're in everything, in all life forms, us, everyone, they're everywhere. The way they're classified is in these CYP families. So they're given numbers, so like CYP1 to CYP9 are manuals, CYP10 to CYP69 are like fungi and all growing eukaryotes, and so on and so on. Okay, so as I say, we work on just one particular class of these, CYP74. So what about the functions of P450s in mammals? So I've done this to try and illustrate the actual very close similarity in function between animal and plant P450s. So in mammals, the role of P450s is generally to metabolize antibiotics, so foreign compounds that the that we may encounter. So these can include like environment compounds in the environment, pollutants, natural products. They're involved in making cholesterol, steroids, prostacyclins, thromboxane. And they're very important in human disease. So any mutation in P450 genes can cause very severe human diseases. And they can convert pre-carcinogens to carcinogenic compounds. And of course they play a major role in drug interactions. So the substrates of P450s are actually all these particular drugs. So you can see they're of massive interest to the drug industry. So an impressive fact about P450s in drugs is that there are just 2 P450s in humans, but they metabolize 90% of the drugs in clinical use, which is actually potentially a problem. So what about in plants? Well, as you might expect, plants also get exposed to antibiotics, and indeed P450s in plants do essentially the same thing. They metabolize antibiotics. So again, they include things like environmental compounds, pollutants, natural products, but they also might be things like herbicides, man-made compounds that they may encounter. And they involve enzyme systems to deal with these compounds, to break them down. And they're involved in the synthesis of a huge range of chemically diverse natural products. So all these different types of compounds have all been shown to be regulated by P450 enzymes. The one thing I want to discuss is the CYP74 enzymes. The CYP74 enzymes produce these compounds called oxylipins. And green leaf volatiles is a term that's sort of adopted in the States really to refer to these compounds that appear on the surface of leaves. They can be detected above leaves that are infected with pathogens. You can see things emerging from the leaves. We call them oxylipins. And let's talk to you about how they're synthesized in the plants. So the very first step in the synthesis of oxylipins requires this enzyme called lipoxygenase. So what happens is, in response to developmental and environmental cues, there's a lipase-mediated release of these polyunsaturated fatty acids like linoleic acid or linolenic acid. And these are, in the presence of oxygen, these compounds are converted to these hydroperoxide compounds. And these hydroperoxide compounds have got a specific, the positional isomers. They can be oxygenated to position 13 or position 9. And depending on whether they've got number of double bonds, they can be diadoinic acid or trinoic acid. And then this enzyme I work on, this hydroperoxide lyase, then uses these products of LOX metabolism to actually convert them to these green leaf volatile compounds. So these are the hydroperoxides that are produced by lipoxygenase. And then what can happen is there's various enzyme systems in the plant that can convert these into various things. There's an enzyme called allyl oxide synthase, which will convert this into an allyl oxide and onto 12-OPDA, which goes on to form jasmonate. And jasmonate is very important in signalling in the plant, cell signalling. Alternatively, these enzymes can be converted by the hydroperoxide lyase. And this enzyme converts them to oxidodecanoic acid. And through the action of an isomerase, we're not entirely sure how this reaction goes ahead with it, but it may be a non-enzymic reaction. But essentially you can also detect this compound called traumatin, or wound hormone. But the major product are these 6-carbon volatile compounds. The typical one is like this cis-3-hexanal. Another way they can be converted is by an enzyme called diamine synthase, which converts it to a compound called chondrolenic acid. And again, these have been shown to have physiologically important roles. The enzyme I'm going to talk about today is the hydroperoxide lyase, and all you need to know really is that HPL products help defend plants against pathogens. So this compound here is directly antimicrobial. It can be shown to be antimicrobial, and so can these. So they're not necessarily involved in signalling, they can actually inhibit the growth of pathogens as well. So maybe just in passing I should mention, so you know when you mow your grass, the typical smell that you get is often a result of the action of this enzyme. So you're looking at a response of the plant to mechanical damage. It's set as an attack and it's just responding to that response. So what is the source of HPL? Where can you get HPL from? Well, it's very difficult to get it from the plants because in the plant the protein is produced in very tiny amounts. It's an incredibly active enzyme, so the plant doesn't need very much of it. But it's very difficult to purify and handle. So what we've done, we've we produce a recombinant HPL from the plant Medicargo truncatula. Obviously coming from John Ennis, the only reason why we've got it from Medicargo is because the genome's in the sequence, and obviously they're the sort of plants we work on. But it doesn't really matter where the enzyme comes from. The enzyme is from Medicargo, and we produce it E. coli. And I just want to summarise, the enzyme that we produce has been extremely well characterised. So it shows a typical UV visible spectrum of a nice P450 enzyme. And unusually, you can produce this P450 very well in E. coli. So a lot of P450s, you can't do this in bacteria. You have to do this in either a yeast system or a mammalian expression system, or in insect cells. But this one expresses really well. You get it's a histag protein, so you can see that when you purify it, the columns go literally dark brown because there's so much protein being produced, and it's very pure. It's a lovely monomeric enzyme, very nice single species. All the kinetics have all been done, and we've published quite a few papers in this area showing that how to characterise this enzyme and show that this what this enzyme is doing. So just to summarise the work we've done, we've basically shown that the enzyme is actually a monomer, but it's complex with the detergent micelle. So this enzyme is actually naturally membrane bound in the plant. It's a peripheral membrane protein, so it's not integrated into the membrane. You need detergent to extract it from E. coli, but it doesn't actually associate with the hydrophilicity of the membrane. We know that if you bind to a membrane or a detergent micelle in an in vitro environment, that you induce a conformational change in the protein, and that actually improves the substrate binding and turnover. And this, we've published a new mechanism. This is actually a new mechanism for regulating the activity of a cyclone P450 enzyme, which hasn't been seen before. We've shown that it's biologically relevant, so you can actually show in the plant, using purified lipid bodies from the plant, you can actually activate the enzyme. So it's a biologically relevant process. We've shown that the enzyme's got very broad substrate specificity, which actually is quite useful in the idea of using it as a biocatalyst, because it can work on both 9 and 13 hydroperoxides from both linoleic and linoleic acids. There's a whole potential for a whole range of different chemistries to go on. The one really impressive fact is this is one of the fastest enzymes recorded in nature. It's got an enormous turnover number of about 4,700 per second. So you think this makes sense. I mean, in nature, the plant wants to respond very quickly to producing these volatile compounds to inhibit any pathogen. So this is exactly why it works so quickly. And like I say, for industrial biotechnology purposes, it makes it an ideal biocatalyst, but you don't need very much of the enzyme. People talk in terms of grams per litre, but really you don't actually need that much of this enzyme. If you get a few milligrams of this enzyme, you will get shed loads of product. And the one key thing that makes it a really good biocatalyst is that this enzyme is essentially dormant until you add detergent. So you can purify this enzyme in the absence of detergent, and it's not very active. And as soon as you add the detergent to it, it spontaneously gains massive activity. So, what are the current uses of these HPL products? So, as I say, these are classed as green leaf volatiles, and they're used in the food industry because of the fresh green odour of these compounds. And what they do is they're often used in restoring the freshness to food. So I know it sounds awful, when they process food, they sterilise it, it often loses its the smell, so they can put these compounds back to regain the nice fresh green smell. And they're used extensively in the food and beverage industry to add organoleptic impact products. It's, like I say, it's a very versatile catalyst. So starting from, this is the pathway, so starting essentially from something as crude as vegetable oil, which is rich in linoleic and linoleic acid, you can pretty much go to all these other compounds. You've got all these particular aromatic properties, and you can even produce things like the smell of old leather if you're that way inclined, if you're interested in that. So the ability of obviously this enzyme to make such an array of different aromatic compounds has made it a hot property for patenting. And there's been a whole load of patents that have been published since 1995 to actually protect the intellectual property on this enzyme. They've seen the potential, the value of it. But despite all this, the use of HPL as a biocatalyst hasn't been fully exploited. And why is that? Well, pretty much, as I say, the main problem is it's present in tiny amounts in plants,